Hello guys, and welcome to our A classes for General Physics 2. Today's lesson will be on capacitance and current electricity. So what are capacitors? Capacitors are condensers, which is a device used in storing energy. Essentially, all capacitors consist of two metal plates separated by an insulator, which are encapsulated in dielectric media. The insulators in are called dielectrics. Dielectric materials can be solid or liquid. Yes, we have solid dielectric capacitor, and we have solid dielectrics, and we have liquid dielectrics, depending on the material we're discussing about. The symbol for a capacitor is just two equal straight parallel lines here. This represents a capacitor. Here we have some types of capacitor. We have what we call a mica dielectric and a paraffin wax paper dielectric. The capacitor itself with the symbol TT, a tin foil with dielectric material, the mica dielectric material inside the tin foil. In this case, it's a paraffin wax paper dielectric, a tin foil, and it's a paper paraffin wax inside as a dielectric material. Capacitors in AC circuits. Capacitors are widely used in AC, alternating current, and radio circuits. They can transmit alternating current. When you look at the diagram, when key A is closed, current flows from battery X to charge the capacitance D here. And when you close key B, open up this and close key B, current now flows from battery Y to charge D. If you interchange the switches intermittently, tap, 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 current flows back and forth along the wire connected to the capacitor. The ratio of the charge on either plate to the potential difference between the plate is what we call capacitance of the capacitor. Simply written as C, the capacitance, is equal to charge all over voltage. So C is charge over voltage, means our charge is capacitance times the voltage, and the voltage charge divided by capacitance. And it's important to know that 1 microfarad is the same thing as 10 raised to the power minus 6 farad, while 1 picofarad is 10 raised to the power minus 6 microfarad, which automatically means it's 10 raised to the minus 12 farad. For example here, which I expect students to solve based on the formula here for capacitance, is a direct question. Calculate the capacitance of a capacitor whose charge is 2.2 coulomb, operating with a potential difference of 1200 volts. Just plug in this value into the equations and you'll be able to get the capacitance of the capacitor. I expect students to do that and tell me what the answers are by the time we meet in our lesson. Comparison of capacitance. Experimentally, you can compare capacitance and we are able to determine an unknown capacitor during experimentation using what we call the ballistic galvanometer method. This is the ballistic galvanometer. We have a capacitance C1 and then key 1, key 2, lock of the key 1. We have a cell here. So using ballistic galvanometer, large capacitances can be compared. The capacitor of the capacitance C1 is charged by a battery of EMF V volts, battery here. Record first deflection Q1. When you close this key, record the deflection. So you are recording what happens during charging of C1 from the galvanometer. So record that and call it Q1. Then discharge. By discharging, you're opening the key to discharge. Then replace C1 with C2. So remove this capacitance, bring in C2 capacitance and add into this connection. Charge and record Q2, then discharge. So if C2 is the standard capacitance and its value is known, then C1 can be calculated. How? We know already that Q1 over Q2, which is the charges, charge 1, charge 2 is same thing as Q1 over Q2. Therefore, C1V over C2V is equal to Q1 over Q2. If C1V, because Q1 is charged at voltage and Q2 is C2 charged at voltage, and they are equal to the Q1 over Q2. The voltage and the voltage will cancel out. You will be left with capacitance 1 divided by capacitance 2, which is equal to the deflection for the first reading and the deflection for the second reading. So if we know the value of C2, we'll be able to determine the value of C1. Because this is known, we know this deflection, then we'll be able to calculate this. It simply means that C1 is C2Q1 divided by Q2. That you can try from my explanation, and by next class we'll be able to explain what you get. Factors determining capacitance. What are those factors that determine capacitance? There are three basic factors that determine the capacitance of a capacitor. This is a capacitance or a capacitor. You have two plates A and B, and then you have, if you measure there is distance between point A and B, you have the dielectric medium, the medium that is between them. It could be solid, it could be liquid, remember. Then the area between the plates. So it means these are the three main factors that affect the capacitance of a capacitor. So distance between the plates, the dielectric of the medium, and the area of plate. So the capacitance is directly proportional to the area of the plate and inversely proportional to the distance between the plate. The permittivity here is in relation to the dielectric. So the higher the permittivity value or dielectric value of the medium, the larger the capacitance. The larger the area, the larger the capacitance. But the smaller the distance, the larger the capacitance. So the higher distance, the smaller the capacitance. Capacitance values, concentric spheres. We'll look at the potential difference between concentric sphere A and B. The smaller sphere has radius of A and the larger sphere has the radius of B. The inner sphere has a positive charge while the outer sphere has a negative charge Q. So if you put that into perspective and you begin to look at the calculation, so there's the potential difference. The potential difference between the two is going to be VA minus VB. And because we are discussing potential difference, which is electron volt or electric field intensity, remember it's 1 over 4 pi E naught, which is KQ over R squared. So 1 over 4 pi E naught, the charge of smaller sphere minus the larger sphere divided by their radiuses. If you simplify this, you have voltage equals to Q, because the QQ here it comes out, Q equals to 4 pi naught B minus A over B. And we are trying to look for the capacitor, which is charge over voltage. So you make this solid to the formula, then you are going to have 4 pi E naught AB divided by B minus 8. To get the capacitance from here, it means our capacitance is going to be 4 pi E naught AB over B minus 8. If you have this data, you can be able to calculate the capacitance. For example, suppose B is 10 centimeter and A is 9 centimeter, and and you are asked to, in this circle, A here is 9 centimeter, while B is 10 centimeter. Plug that into this equation. You are going to have 4 pi E naught AB. So 4 pi E naught, the value of the permittivity 8.85 10 minus 12 bar per meter times 0.1, the B, divided by 100, gives 0.1, 9 centimeter divided by 100, 0.096, divided by B, 0.1 by 0.09, and you do your calculations, you are going to have about 100 picofarad. For an isolated sphere, the capacitance is just V equals to charge divided by 4 pi E naught R. Remember our last lesson where we said the electric field intensity for an isolated sphere is charge divided by this. The same thing we're talking about here. A charge all over voltage is what? The capacitance. So capacitance charge over voltage is equal to 4 pi E naught R, and therefore our capacitance is 4 pi E naught R. Because this charge comes down here, we'll be able to cancel out with this charge, and then you'll be left with this. Example, suppose R is 10 centimeter, which is 0.1 meter, then the capacitance is 4 pi E naught R. So just plug in the value of R in the equation, 0.1 R there, 0.1, and everything is in farad. And you end up having 11 times 10 minus 12 farad. Yet it can be converted to 11 picofarad. Remember, 1 farad is equal to 1 times 10 minus 12 picofarad. Parallel plate capacitor. Suppose two parallel plates of capacitor each have a charge Q. The surface density given as, remember our surface density in our last lesson, the charge is surface density times area. Therefore the surface density is charge divided by area. And electric field intensity, if you have not forgotten, is the surface density divided by the permittivity. And then bring in the value of surface density into this equation. You are going to charge all over area. So the electric field intensity for parallel plate capacitor is charge divided by area times permittivity. While the voltage across the plates will be voltage is equal to what? Charge, voltage equal to charge times the area or capacitance here. And while we have said this is capacitance, so voltage now is the charge AE divided by D, and the voltage across the distance between the two plates. Charge divided by voltage is EA over D, where is the permittivity, the area of the plate, and the distance between them. Therefore, capacitance, because this is capacitance, C is equal to E all over V. Capacitors arrangements. Parallel capacitors, you know when capacitors in parallel. This is parallel arrangement of capacitors and then connected to a battery cell. Q1, C1, Q2, C2, Q3, C3, and you're asked to find the total charge or total capacitance of this circuit. Q1 is C1V, Q2 is C2V, Q3 is C2, because it's a common voltage across them. Look at the voltage. This is common across all the three capacitances. So the total charge on the system is going to be Q1 plus Q2 plus Q3. And if you come to how we have separated them here, Q1 is C1V, Q2 is C2V, Q3 is C3V. So, and the V is common among all. We are going to have C1 plus C2 plus C3V as the total charge in the system. So if this is the total charge in the system, then the capacitance is going to be charge over voltage. So our charge is C1 plus C2 plus C3V divided by V. It takes away that V. So this is the total capacitance of the capacitor in this circuit. For parallel arrangement, the total capacitance for a capacitor in parallel arrangement for three capacitors is just C1 plus C2 plus C3. If it's in series, look at series arrangement. This is C1, this is C2, this is C3. A, B, C1, D, F, C2, and GH, C3. Each one of them have its own potential difference VAB, VDF, VGH with another common voltage across the three. So for VAB, the potential difference is charge divided by capacitance C1. For VDF, which is this, the potential difference is charge divided by C2, because the charges are, look at the charges are just between Q plus, Q plus, Q plus. And then for VGH is the charge divided by C3. The sum of this is equal to the applied potential difference V, because the work done in taking any charge from H to A, is the sum of the work done in taking it from H to G, from F to D, and from B to A. So what happens from this point to this point is the same thing as moving from this point, and this point. So it then means that the voltage, the total voltage in the circuit is the sum of this voltage, and this voltage. So you are having V equals to VAB plus VDF plus VGH, which have been defined here clearly. Q over C1, Q over C2, Q over C3. Looking at them very well, Q is common in all, and therefore our key comes out, Q comes out here. So our potential difference V now will be Q equals to 1 over C1 plus 1 over C2 plus 1 over C3. V. Remember, capacitance is voltage divided by charge. Capacitance is charge divided by voltage, or 1 over C is V over Q. So hence, from equation 3, 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. In series arrangement, it's just C equals to C1 plus C2 plus C3. And let us look at a common example here. Find the charges and capacitance in the figure and the potential difference across them. Capacitance between points A and B. To find C1 or C prime is C2 plus C3. This is C3 here, capacitor C3, and this is C2. Total capacitance here. These two capacitors here are in parallel. So the total capacitance in parallel is going to be C2 plus C3 parallel arrangement, 3 microfarad. Because this is 2 and this is 1. So just add them up here, we have 3 microfarad. The overall capacitance from point A to B, this and that capacitance now at B. So is this and this now in series. For series arrangement, it's going to give you 1 all over C. I call this one C1. So 1 over C1 plus 1 over C prime. When you do the calculation, this is what you are going to have. Total capacitance is going to C1 C prime divided by C1 plus C prime. You have 2 times 3 divided by 2 plus 3, 1.2 microfarad. So capacitance across point A to B is 1.2 microfarad, while between these 2.3 microfarad. Charge stored in this is Q1 equals to Q2 plus Q3, Q2 plus Q3. So Q1 here gives you what is inside here, Q2 plus Q3, which is CV, which is this 1.2 times this value, total capacitance of the whole circuit, 1.2 microfarad from point A to B, because that is the total capacitance we are talking about in this circuit, times the voltage across 120 volts. So you end up having 144 times 10 to the power minus 6 coulomb, or 1.44 times 10 to the power minus 4 coulomb. For voltage C1, for voltage V1 is Q1 over C1, put those values and divide by the capacitance C1. So our V2 now will be V minus V1, you have 48 volts. The Q2 is going to C2 V2, which is this 96 times 10 minus 6 coulomb, and Q3 is going to be C3 V2, 10 to the power minus 48 times 10 raised to the power minus 6 times 48 equals to 48 times 10 to the power minus 6 coulomb. Energy of a stored capacitor. And let us suppose that we wish to increase the charge on it from q to plus dq, where dq is very small. Then a charge dq from the negative plate must be transferred to the positive. In doing this, the potential difference is increased by dv equals to dq over c. Instead of v equals to q over c, now dv over dq over c, that increase. But if dq is very small, the work done now is v dq. From definition of potential difference, v is charge over capacitance. Therefore, our work done, since it's v dq, put the value of v, which is q over c, so q over c dq. So the total work done is to take the integral of the work done from point q equals to q1, point q equals to 0. You are going to have q dq over c, which will give you half integral. Your mathematics physics, mathematical physics or maths 101, which you have to understand this. Q squared over 2, and you have 1 over q1 squared all over c, or q squared over c. You need to add the 1. So the work done generally therefore is half q squared divided by c. And half q squared divided by c is same thing as half qv. Why qv? Q is still there, and vq, q is there, another q over c, c is q over v, so and you have another c, you have qv, which is same thing as half cv squared. So what we have just expressed, you can do this mathematics, follow it carefully, follow the formulas, and see how it is solved. That it has been solved, just follow what as a guide and see what it will help you do. Same thing here, it goes along until you get the final total energy of the capacitor. And now another question, you say two capacitors of 4 microfarad and 2 microfarad respectively are joined in series with a battery of EMF 100 volt. What is the capacitance of the capacitor? Find the total charge in the circuit. The question is, they are in series. And they are in series, 1 over c is equal to 1 over c1 plus 1 over c2, which is 3 over 4, because it's 1 over 4 plus 1 over 2. LCM is 4, 3 over 4. Therefore, c is 4 over 3 microfarad. Remember, our charge is CV. So, to get the total charge in the circuit, charge is equal to CV. The C we know is 4 over 3 times the V, which is giving 100 volts. Put that value, you are going to have 133.33 coulomb. Yes, it's been a little bit tough. You understand this more by the time you go back to the drawing board and physically solve it out. Just follow the procedure on the video and I'm sure you will get it right. We'll meet again to explain further on this course. Thank you very much. God bless. Bye-bye.